Hello, my name is Shuang Lim and I'm from Physics at NC State University. So I would like to talk about and share my results on mechano-sensitive upconversion nanoparticles that can sense forces in different directions. And our envisioned application of these nanocrystals are in biotherapeutics, force sensing in tissue, and also for structural health diagnosis in structures like metal structures in ships and on airplanes, and in particular at the interlaminar layer between dissimilar metals. So what makes this force sensing possible in these nanocrystals? So we can see here these are hexagonal crystal structure of upconversion nanoparticles, and the structure shows that the orientation of all the ions are anisotropic. So this results in a local crystal field, and so the dipole oscillator strength varies along the different axes of the nanocrystal. So that means that when you apply a force, and the force in different direction, that leads to compression of the crystal structure, and the distance between ions are different, they change, and this results in a change in the spectra of the nanocrystal. So the force response will be orientation dependent. And so when within the nanocrystal structure, the ions are compressed and put in closer proximity, then there is a stronger orbital overlap, and that changes the spectra of the crystal. So we can correlate the change in spectra with the applied force. And so these crystals are different compared to the traditional fiber optic sensors, because in fiber optic sensors, the sensing is along the entire length of the fiber. So when the fibers are integrated into a system, so usually the fibers are bent, and the bending of this fiber puts stress at specific locations of the fiber. So one has to correct for the strain and stress of the bent parts of the fiber. So there's a lot more correction that needs to be done, and also the entire length of the fiber is affected by fluctuations in temperature and strain of the system, whereas in these nanocrystals, one can measure the localized stress of the system. And also in comparison to molecular sensors sense the overall change in intensity of the applied force, but not the direction of the applied force. So we envision that these nanocrystals can sense the applied force in different directions. And so in our experiment, we have mounted the nanocrystal at the end of a fiber tip. So the intention is to be able to excite the nanocrystal and collect the emitted light with the same fiber tip. And we see here, when we have mounted, we have pressed the fiber tip onto the nanocrystal under white light, and then the white light is switched off, and then we excite with infrared light, and we can see the nanocrystal glowing or emitting, and this emitted light is collected by the fiber tip. And then we can analyze the spectra as we press upon the nanocrystal with different calibrated forces. So in the bigger scheme, we have the nanocrystal mounted onto a cover slip, and the fiber tip being pressed with a calibrated force on the nanocrystal, and this light is then collected and then recorded through our spectrometer, and then detected by our APD detector. So we are able to collect the spectra in real time as the force is applied onto the nanocrystal. So we can apply a forward and reverse force. So from our results on the thulium doped nanocrystal, we can see that as the force, applied force is increased, there's a spectral shift to the right with increase in the applied force. And we also see that this increase in the force result in a linear change in the peak shift. So that means that as we compress the nanocrystal, the ion atomic orbitals overlap more, and then this changes the oscillator strength of the transition and also lead to the peak shift. So I want to emphasize that this peak shift is very significant. We get a peak shift of between 5 to 10 nanometers, which is fairly large. And this is in comparison to previous studies done in a diamond anvil compression, hydrostatic compression process, where the compression is in 3 dimensions. And in that experiment, only a very small peak shift was observed. But this is in comparison to our experiment. We only applied a force in a uniaxial direction, and we get a much more pronounced and larger peak shift of between 5 to 10 nanometers. So further, we performed the experiment on an erbium doped nanocrystal, and we see again a peak shift as we increase the applied force in the uniaxial direction. But however, we see 2 regimes of peak shifts. So when we plotted the shift in the wavelength with the applied force, we see 2 different regimes, and this clearly tells us that there is an apparent pressure-induced phase transition under the uniaxial strain, and this has not been observed before until we applied our uniaxial force loading scheme. So other than the large peak shift of between 5 to 10 nanometers, we see this change in slope. Then this suggests that there is a abrupt phase transition after a critical uniaxial force is reached. So in order to demonstrate the mechanosensing response of our nanocrystals in a biologically relevant medium, we repeated our experiments in aqueous media and in deionized water and also in phosphate buffered saline. Then our results unambiguously show that the spectra remain unchanged when we perform in aqueous media and also after drying. So this shows that these nanocrystals are very stable and they are not affected by the external medium. So we suggest that the optical mechanism as to why these nanocrystals are sensitive to applied force is that's because this nanocrystal is anisotropic. So the dipole oscillator strength varies along the different axes. So the force response will be orientation dependent. So as we apply varying force intensities at different magnitudes, there will be a local symmetry distortion and a change in the interatomic distance, and hence the overlap between the atomic orbitals. And this would then give rise to the peak shifts that we've seen and also the apparent phase transition that we have observed. So in the future, in order to confirm the local symmetry changes, we need to measure the Raman spectra of these nanocrystals as they are undergoing compression. And we also plan to substitute some of the ions in our nanocrystal with the manganese 2+, which have been known to increase the force sensitivity. And so we expect that when we substitute with a different ion like manganese 2+, we expect a peak shift in our Raman spectra. And further, We also want to vary the dopant concentration in our nanocrystal, because we expect that as we increase the dopant concentration, that we will give rise to a increased disorder in our nanocrystal. And this disorder can be detected with Raman measurements. So we expect that if there's greater disorder in our nanocrystal, there will be significant peak broadening with the dopant level. And at the same time, with the increased dopant concentration, we will generate different phases, possible different phases, such as secondary phases within our nanocrystal. So when the secondary or phase is generated, we would expect to see new peaks in our Raman spectrum. So from our current work, we have plans to measure the nanocrystal response at interlaminar layers within metals. And in our scheme, currently in progress, we have the metal layer coated on a sapphire substrate with the nanoparticle at the interface. And so we have been applying forces and measuring the nanocrystal response to the different forces at the interlaminar interface. So this work is made possible with contributions by our group members, and which have been juggling the research and family life during COVID, and they have done a great job and a marvelous effort at balancing both work and play. And I would like to acknowledge the funding sources from NSF and also the contribution from the NC State NNF facility in our work. Thank you very much for your attention.